Alright, welcome back to part 2 of our theory workbook. So let's take a look at the questions on stability and center of gravity. So let's look at question 2 first. The diagram shows a thin irregular shaped piece of aluminium sheet of uniform thickness. It hangs freely from a nail at position X. An iron block is then attached to the bottom, which position is likely to be the center of gravity of the setup. So if we were to look at the object here, we can find the center of gravity not by the geometrical center. We can find the center of gravity by using a plumb line. You hang it at point X. You take a string, you let the string drop down, and then wait for it to swing and then stabilize ready. The string should cut through here. Okay, then you poke another hole, another corner here, maybe down here. Okay, at the other corner here, and then you flip it up, hang it by this dot here, and then you let it swing, and then it should be cutting through here. Okay, and you do it, repeat for the other side. You repeat for the other side itself. If you do it here, you hang, take a string, let it swing and stabilize. You will get it about here. So the center of gravity now is at C. This is without the iron block. Now, if you were to put the iron block, something heavier here, what will happen to its center of gravity? Something heavier, you place it at the bottom. Good. You lower the center of gravity. So in this case, from C, you lower. The only other next possible option would be D. Okay. So let's look at question 3. Question 3, there are two egg shapes, have a piece of lead embedded in them. Which of the following correctly describes the type of equilibrium? So two eggs here. Originally, their center of gravity should be here and here in the middle, but because they have lead inside, the center of gravity are shifted. So this one will be shifted up higher. This one will be shifted down lower. Okay. So they ask, what type of equilibrium are they? So they're talking about the stability. If we were to give this a push, okay, what will happen is subsequently your egg has the folding base on it. So this is the area in contact, or what we call the base area. It's very, very small. So what will happen is your center of gravity X now will be here, and your weights will act here. Now, as you can see, the line of action, so let's draw the line of action of this weight, is outside the base area. So this line of action of weights is outside the base area. What will happen is this will give it a anti-clockwise moment, and then your item will swing downwards. Okay, so in this case, this will be unstable. Another clue is also to look at center of gravity. One moment is high, next moment as it falls, your center of gravity will drop. It will drop, it will drop, it will drop down. Okay, so center of gravity gets lower and lower as another sign for being unstable. Center of gravity goes low. Okay, next one, let's look at object Y. If we were to give it a slight push, what will happen is it will swing up and then come back down. Let's swing it the other side, it will be the same thing also. So in this case, what will happen to the center of gravity is center of gravity will move up and down. That's why it's stable. Neutral means center of gravity unchanged. The height of center of gravity. But in this case, if you are to tilt it, your center of gravity may be higher. So the egg, if it tilts, oops, I can't draw this well. Okay, you get the idea. So center of gravity will be higher, then it comes back down. Because there's a change in the height and it returns back to its original position, it is considered as stable. Let's look at question 4. So question 4 here, there is a toy bird that is pivoted and stable equilibrium. They want to find the center of gravity, which position A, B, C, D shows the center of gravity of the bird. So you want it to be stable, you want it to be in equilibrium. So if it's at A, if I were to push the bird, what will happen? Center of gravity will fall outside the base, the bird will turn this way, so that it will have an anti-clockwise movement. So A is definitely out. Let's imagine if we put at B. So you put at B, if I were to push, let me erase the previous one. So now if I put at B, I give a push this way. Center of gravity will fall outside the base area, the whole bird will tilt clockwise. So we also do not want B. So let's look at C. So C is here. What happens if I give it a push? It will go down, the bird will turn clockwise. So which is also not good, so we do not want C. So answer will only be D, because imagine D, if I were to push the bird here, push like that, what will happen is this goes up and then comes back down again. Center of gravity will return back to its original position. Center of gravity will also be lower upon being disturbed. Okay, whereas for the rest, the center of gravity will keep uh, getting lower and lower and lower. Okay. Sorry, apologies. I mean that the center of gravity for D will go higher before returning back to its original position. That shows that it's stable. But if the center of gravity keeps getting lower and lower, it means that it is unstable and it will continue to fall. Okay, generating a moment. All right, let's look at question 1 for section B. We have explained already. This is stable. First one is neutral, the last one is unstable. Next one, they want you to explain your answer with the aid of a diagram and comment on the stability of block X and block Y. From what we see, we can know immediately that block Y is much more stable because it has a wider base area. It is lower in terms of its height, also means its center of gravity is lower. So all of these points that is more stable. But we have to draw. So what do we draw? We draw two objects and it is tilted at the same angle. So let's give the angle maybe at about, I don't know, 30 degrees. So both at the same angle. What is the result? Block Y is more stable than block X. Why? Because it has lower center of gravity and it has a wider base. Okay. Next, we tilt it by an angle. The vertical line through its center of gravity falls within its base. So what do I mean? Let's draw the vertical line. So this object here has a weight here. So the line of action will be here. This weight is here. So the line of action will be here. Okay. So you look at X, the line of action is outside the base. Where's the base? This is the base. This is the base for Y. Okay, so which one is outside, which one is inside? Yes, X is outside. This will cause it to have a clockwise moment. And Y is inside. This will cause it to have a anti-clockwise moment. So which will return back to its original position, X or Y? Yes, Y. Because the center of gravity falls within its base, thus the counter moment allows the weight to go back to its original position. So we want to restore it to its original position. However, when block X is tilted, the vertical line through the center of gravity falls outside the base and block X topple. Okay, so this is how we explain in terms of stability. Alright, let's look at question 3. Define center of gravity. Center of gravity of the object is the point through which the whole weight of the object appears to act for any orientation of the object. So that's the definition. Let's look at part B. There's a 300 gram walking stick. It's placed on a pivot. So this is the pivot P. It's 300 grams. Well, we know that this is 0.3 kg or W equals to mg. This will give us as times 10. This will give us as 3 newtons. Okay, I'm doing this so that it's easier for us to get information later. It's balanced by a 100 gram mass. So your 100 gram mass is 0.1 kg or is 1 newton. Calculate the distance of the center of gravity of the stick from the pivot. Center of gravity from the stick. So let's draw it out first. So this object has a weight. Okay. This walking stick is balanced by 100 grams. That means the center of gravity is maybe a center, may not be a center, we do not know. So let's just roughly place center of gravity here. Center of gravity means the weight will act on it. So this is the weight of the walking stick. And the weight of walking stick is somewhere here. The distance from here to here, let's give it as D. And the other distance is 15. So using the principle of moments and taking moments about the pivot, we want to include that the sum of the clockwise moments is equals to the sum of the anti-clockwise moments. Okay, so let's put in the numbers. Clockwise is which? This causes it to turn like that, this causes it to turn like that, this is clockwise, this is anti-clockwise. So which one do we clockwise first, right? Because you want clockwise here first. So clockwise is W, which is here, 3 newtons, times 10. The distance is D, which we do not know. Next, we have a mass here, which is 1 newton, times the difference of the distance of 15 cm. So if we do the math, you can find that D equals to 5 cm. This is just balancing of the moments itself. Okay, so I think with that, we will end the session for today. Thank you.